Larus argentatus, the herring gull, weighing a little over 2 pounds, supported in flight by a wing of 2 feet span, exerting a lifting force exactly equal to its weight. Boeing 747, the jumbo jet, weighing over 700,000 pounds, supported in flight by a wing spanning 195 feet, exerting a lifting force in level flight, which is also exactly equal to its weight. Captain approach of Bravo Charlie Echo Whiskey. Echo Whiskey, ground on approach, go ahead, over. Echo Whiskey, position Newport Blackwell, 2,000 feet. Echo Whiskey, roger, join downwind left-hand runway 26, Quebec. In determining just how an aeroplane flies, and the forces acting on it, its natural behavior and the ways in which we can control it, let us go to the grassroots of aviation. And from a considerable range, take a typical light aeroplane as our example, the Cessna 150 Aerobat. It weighs 1,600 pounds fully loaded and is supported in flight by a wing spanning just over 32.5 feet. This wing, like every other, exerts a lifting force in level flight exactly equal to the weight of the aeroplane. To understand how an aeroplane flies, we need to know something about the air it flies in. What are its properties and how it behaves? This envelope of air that surrounds our planet has certain physical characteristics and patterns of behavior. Though it's invisible, it's made up of molecules like everything else. It has density and pressure, both greatest at sea level, where the pressure averages nearly 15 pounds per square inch. The further from sea level we climb, the lower the pressure becomes. Until at 20,000 feet, it's only about 7 pounds a square inch, and at 60,000 feet, only about 1 pound a square inch. And as the pressure falls, so does the density and the temperature. But that 15 pounds a square inch at sea level is only an average. In fact, the pressure in any given place changes all the time. And as it changes, the air circulates around the areas of high and low pressure, and the wind blows. Now we realize that air is a fluid, seeking its own level like any other fluid. And we can feel the force of its moving molecules as they rush past us and pull at everything in their path. Moving air as a source of energy has been harnessed for centuries with ever-increasing skill and understanding. The aeroplane harnesses the same source of energy by the opposite process, by moving through the air. Let us look at the aeroplane for a moment. It's basically a simple and functional machine. Wings set at right angles to the direction of flight support a body or fuselage to carry the load. Smaller wings and a vertical fin at the tail end of the fuselage provide stability and control. In the nose, an engine and propeller provide the motive power. But it is the wings moving through the air that lift and support the aeroplane. How? To find out, we must first make air visible. We can do this in a smoke tunnel, having first turned it on its side so that we can relate it to horizontal motion. In the tunnel, we can put various solid bodies in the path of the smoke filaments, change their angle to the moving airflow, and see what happens. First, let's take a cylinder. Notice that the airflow curves closely around the frontal curve of its circumference, clinging to it, until suddenly it separates. It can't hold on any longer and becomes unstable and disturbed. It's moving too fast to tuck in behind the cylinder and maintain contact with it, so it has to let go. Now let's take a flat plate. Lying horizontally to the airstream, the flat plate disturbs it hardly at all. But turn the plate across the airflow and see what happens. Turn it back again, and we can see that even at the slightest angle to the horizontal, the airflow over the upper surface tends to break up. Next, a curved plate. This behaves rather better. The airflow is smoother, but it soon breaks away when the plate is rotated through an angle to the airflow. And at a smaller angle, the airflow breaks away underneath where the plate is concave. But if we look at the wing itself, we find that it's neither a flat plate nor a curved plate, but a combination of the two. It has thickness. The underside is almost flat. The leading edge is blunt and rounded, while the trailing edge is sharp. The upper surface is curved or cambered, and the wing is in fact attached to the fuselage at a slight angle to the horizontal. Cut a section through the wing, and it looks like this. If we set it in the smoke tunnel, we can see how smoothly the air flows around its contours. What's more, we can increase the angle to the airflow by quite a large amount without it breaking away. We call this variable angle to the airflow incidence, or angle of attack. But the really important thing is what happens to the airflow as it flows over and under the wing. Here is the airflow again, this time in slow motion and with an irregular smoke flow. Notice how the smoke accelerates as it moves over the upper surface of the wing, while the smoke flow below the wing tends to slow down. This is just what happens in flight, and it is this phenomenon that causes the wing to lift. For when a fluid in motion increases its velocity, its static pressure, which acts at right angles to the direction of flow, decreases. And when the velocity is reduced, its static pressure increases, so that its total sum of energy always remains the same. To prove it for ourselves, we need another kind of wing model. The surfaces of this one are perforated by a number of pinholes. Each pinhole is connected separately by an airtight tube to a manometer tube. Manometers measure pressure. When we drink through a straw, we suck in to reduce the pressure in the straw, and this causes the liquid to rise up inside it. If we alternately blow and suck on a manometer tube, the same thing happens. And so, if we put the wing section into a wind tunnel, any changes in pressure acting at right angles to the wing surface will be shown on the manometer tubes. Each tube is attached alternately to the upper and lower surfaces. Here is the wing section with wool tufts to show us the airflow. Now let's superimpose it on the manometers and see what happens. The manometers attached to the upper surface rise, indicating a considerable drop in pressure, while those attached to the lower surface fall, indicating a rise in pressure. And it's this difference between the pressures over the upper and lower surfaces that gives the wing its lift. In fact, the pressure pattern looks like this, with the pressure at any given point acting at right angles to the surface at that point. The pressure difference is greatest where the curvature is greatest, least where the surface flattens out. The resultant lift force acts through a point we call the center of pressure, and at right angles to the relative airflow. And so we have a cambered wing flying at a small angle to the horizontal, producing a resultant lift force exactly equal to the weight of the aeroplane in steady level flight. Lift increases with speed. We prove it every time we take off. It also increases with an increase in the angle of attack. Let's follow that takeoff through in the wind tunnel. See how the lift builds up with the speed. In fact, it increases as the square of speed. Then as we increase the angle of attack at liftoff, there's a sudden, almost muscular increase in lift to help us off the ground. But the extent to which we can increase the angle of attack to the relative airflow is strictly limited. If we increase the angle by more than a certain amount, depending on the type of aeroplane, this happens. The airflow breaks up over the upper surface of the wing, the pressure pattern becomes unstable, lift decreases sharply. The wing has stalled. This can happen at any speed once the wing has reached the critical angle. Thus we can see that the pressure difference that gives us lift can only be maintained if the airflow over the wing remains smooth and undisturbed. The stall can be demonstrated in the air. The angle of attack is increased until it becomes critical. Lift is suddenly reduced. The aeroplane drops, pitching nose down, and quite a lot of height is lost before normal, controlled flight can be resumed. This can only happen when the relative airflow over the wing regains its normal angle and lift is restored. The stall can also occur in level flight. At normal flying speeds, the angle of the wing to the relative airflow can be maintained whether the aeroplane's in level flight, on a descending flight path, or climbing. Always provided that the speed is within normal limits. But if the speed's allowed to decrease in level flight, lift will also decrease. Then if we try to keep the aeroplane level, it'll begin to sink. When this happens, the relative airflow gradually changes. If the critical angle of attack is reached, the aeroplane will stall and will drop, momentarily out of control. The speed at which the aeroplane stalls will depend on its weight and will increase with altitude as the air becomes less dense. Nevertheless, we must be able to fly slowly, and in particular to land slowly. To achieve this, we can change the characteristics of the wing by fitting trailing edge flaps. These flaps slide out from the wing and curve downwards as they do so. This increases the camber of the wing over part of its span. The upper surface of the wing now has even greater curvature, and the airflow therefore moves even faster, while the obstruction caused by the flap below the wing tends to divert more air over the upper surface, where the pressure is now even lower. In this way, more lift is gained without any increase in flying speed. With the flap fully deployed, lift is still maintained over the wing itself, but behind the flap, the airflow breaks up, slowing the aeroplane down by increasing another force acting on it, the force of drag. This enables us to approach the field at a steeper angle than we otherwise could, which gives the pilot a better view of the landing area, as well as a lower landing speed. Lift is the force that supports the weight of the aeroplane. Lift is generated by moving a precisely shaped and angled wing forwards through the air, causing pressure changes to take place around it. The force that moves the wing through the air is that of thrust. The force that resists its motion is that of drag. Thrust. The principle is that of Newton's third law of motion. To every action, there is an equal and opposite reaction. When we swim, we push water backwards and move forwards in consequence. Action, reaction, equal and opposite. To sustain this balance of action and reaction over greater ranges of speed and endurance, we need more than human muscle. We need mechanical power. To push a boat forwards through the water, we must use an engine-driven propeller to push the water backwards. It's the same with the aeroplane. The jet engine moves the aeroplane forwards by pushing backwards a stream of hot gases with great velocity. The light aeroplane uses a gentler method. An engine-driven propeller pushes air backwards. The aeroplane moves forwards. Action and reaction, equal and opposite. Gathering motion until the airflow over the wing is moving fast enough to lift us off the ground. To create and sustain thrust, the air must be accelerated by the propeller so that it moves faster than the airflow caused by the forward motion of the aeroplane. We can see this in the smoke tunnel with an electrically driven propeller. At rest, the air flows around it. Switch it on, and the air in front of the propeller is drawn in towards the blades and then accelerated backwards at a speed greater than the forward motion of the aeroplane. It sets up a twisting wash in its wake, just like the propeller of a boat, only a lot faster. Thrust can be varied by controlling the power output of the engine. If we increase thrust, we increase speed, but only up to a point. For as speed increases, so does another force acting on the aeroplane, the force of drag. On days like this, we can see drag at work on any highway. Eddying air swirling behind the moving vehicles, wasting their horsepower and their fuel by holding them back, producing a chaotic pressure pattern like this. Drag can be measured. Take a disc of given area and put it in the mouth of an open wind tunnel. Mount the disc on a sprung slide attached to the indicator arm of a calibrated gauge. The airspeed in the tunnel is measured by an airspeed indicator. Notice first that as the speed increases, so does the drag. In fact, the drag increases as the square of speed. With the airspeed indicator steady at 100 miles an hour, the drag on the disc records a value of 5 on the gauge. If we mount a disc double the area of the first, the drag gauge records a value of 10 at the same airspeed, double the drag. Finally, if we mount a disc only half the area of the first and a quarter of the area of the second, we get a reading of only 2.5 at the same airspeed. So the amount of drag depends on both the frontal area of the disc and on the speed of the airflow. However, aeroplanes nowadays can present very large frontal areas to the airflow and somehow manage to fly around at over 600 miles an hour. So there must be an answer. And there is. Streamlining. If we add a bullet-shaped nose to the medium-sized disc, the drag reading at 100 miles an hour is reduced from 5 to just over 1. Add a streamlined tail, and it goes down to less than 1. The drag arising from the shape and size of an aeroplane is known as form drag or normal pressure drag. And if the shape is sufficiently streamlined, the size doesn't matter so much. One obvious way of streamlining an aeroplane is to give it retractable landing gear and eliminate struts. The results of cleaning up the form in this way are often worthwhile, both in terms of performance and fuel economy. But if the gear has to be fixed, then the answer is to streamline it along with the rest of the aeroplane. Another kind of drag that also increases with speed is that of skin friction or surface friction. This is caused by molecules of air clinging to the whole surface area and combining with pressure drag to hold the aeroplane back. We experience both these forms of drag in water. As we move about, we can feel the pressure resisting us. And at the same time, the water molecules in contact with our skin tend to move with us and try to pull the surrounding water along with them. Even when we streamline ourselves and apply thrust, we can still feel the water clinging to us as we move. In a stream of air, it's this clinging layer of molecules in contact with objects in its path that tries to move them and carry them away. If we pour a light, easily flowing liquid over the leading edge of an aeroplane's wing and then take off, we can see that as the aeroplane accelerates, the liquid tends to ripple as the molecules in contact with the surface of the wing try to hold on to those immediately above them. As the outer layers gradually let go, we're left with a thin, slow-moving film of liquid at the surface itself. It's this clinging of the so-called boundary layer to the surfaces of the aeroplane that enables the pressure changes around the wing to give us lift. Pressure changes that also produce drag. Lift and drag are thus inseparable, but the drag component can be reduced, both by clean design and by keeping the aeroplane clean and polished, thus increasing its efficiency. A third source of drag increases in inverse proportion to the speed of the aeroplane, at its greatest when the speed is lowest. We call this induced drag, or trailing vortex drag, and it arises from lift. As a result of the pressure difference between the upper and lower surfaces of the wing, air tends to spill over the wingtips from the area of higher pressure below the wing into that of lower pressure above the wing. The two air streams meeting just above the wingtip form vortices, a corkscrew pattern of twisting air that produces a considerable amount of drag. At whatever speed the aeroplane is flying, however, the sum total of drag is equal to the thrust being exerted by the propeller. Water skis can help us to understand this principle. The skis give us lift and drag. The motorboat provides thrust. When the two are accelerating, thrust will be greater than drag, until drag increases as the square of increasing speed and the two forces become equal. They'll remain in equilibrium for as long as the speed remains constant. Then, as speed is reduced, thrust becomes less than drag, and the balance is lost. On an aeroplane flying in steady, level flight, the total drag force is always equal and opposite to the force of thrust, in just the same way as lift exactly equals weight.